Hello everyone. Welcome to this last module regarding limits. In this particular video we will introduce the idea of limits ad infinity as well as that of horizontal asymptotes. By definition, the horizontal line y equals L is a horizontal asymptote of the function y equals f of x when either the limit as x tends towards infinity of the function equals L, or the limit as x goes towards minus infinity of the function equals L. Essentially, these limits are indications that as we go towards the extremities, the function's y values will converge towards a specific number. For instance, in this example, we see that as x goes towards infinity, so when we tend towards the extreme right-hand side, the y values of the function are approaching the horizontal line y equals 3. So essentially the limit as x goes towards infinity for this function is 3. The fact that it reaches 3 or not is irrelevant, just like in all other limit cases. It's about what the function is trending towards. For limits, x going to infinity or minus infinity, direct substitution is slightly more delicate to apply than it was the case for x heading towards a. Remember that infinity is not specifically a number, but rather an expression to represent something that is growing in size, but not necessarily in sign. Nonetheless, for many functions, there are predictable trends that will allow us to evaluate these limits at infinity. So here are trends that you want to keep track of. Maybe take note of them and try to remember them as you progress throughout the course. One thing's for sure, an infinite number with a positive exponent, which is the first trend that we observe in our list, will head towards infinity. For that reason, k divided by infinity to the end will tend towards 0. We're dividing k by a really, really big number. Minus infinity to the power n will trend towards minus or plus infinity depending on whether n is even or odd. As for exponential functions, this may depend on the base, since when the base is bigger than 1, the exponential function is one that is increasing, and therefore a as we go towards infinity, a to an exponent that is infinite tends to infinity, but a to an exponent that is minus infinity will trend towards 0. The exact reverse is true when the base is between 0 and 1. Just to highlight those two scenarios, here is an exponential function with base e. Basically, it's the function y equals e to the x. Notice how it is heading towards infinity in height as x goes towards infinity, so as we head towards the right. When we head towards the extreme left, the y values are heading towards 0. So y equals 0 is a horizontal asymptote of the exponential function at the left edge. The exact opposite trend is observed when we look at an exponential function with base 1/2, so a base between 0 and 1. It is a decreasing function that is actually decreasing at a rate of 1/2 for every step forward. And what is happening here is as x goes towards plus infinity, the exponential function is going to 0. However, as x goes to minus infinity, you observe that y values are actually growing. Other infinite trends include the roots. So in this case, the nth root of an infinite number is infinite. The nth root of a negative infinite number is minus infinity, as long as we are talking about odd roots. Logarithmic functions in base e or in base 10 both become infinite at their right extremities. We need not discuss their left behavior since the domain prohibits us from going to the left. Here's an example where we are describing the number of students that are infected with the mad cow disease, and the function n of t equals 60 times 1 minus 2 to the minus t represents the number of infected students. T is counted in days spent at Marinopolis. Find n, so find the number of infected students when t is 1, 2, and as t goes towards infinity. Obviously, counting n for a t of 1 or t of 2 has nothing to do with limits. These are really just direct calculations. N at 1 is 30, and at 2 is 45, which means an additional 15 students were infected in the course of that one-day period. As t goes to infinity, now we're looking at a limit process, where n of t still stands for 60 times 1 minus 2 to the minus t. You've noticed that by direct substitution, 2 to the minus t has become 0. And that's because when we do direct substitution, an exponential function with base a, in this case 2 to the power minus infinity, goes towards 0. So this is, here we're applying the list of special identities that we stated earlier. Graphically, here's our evolution of the number of infected students, going from 30 to 45 between time 1 and time 2. And as we move forward, the number of infected students will eventually flatten out. Therefore, y equals 60 is a horizontal asymptote of the function y equals n of t, since the trend of n of t as t goes to infinity is to head towards 60. Quick true or false question. All polynomials have infinite behaviors at their extremities. So think of quadratics, linear, cubic functions. Is it true that they are infinite at their extremities? The answer is true. Just a reminder that polynomials are expressions whose form is constituted of a combination of constants or coefficient, so constant multiples of powers of x. So if x is heading towards infinity, is the limit applied to the polynomial, one thing we can do is to factor out x to the power n. So this is not traditional factoring in the sense of finding linear factors, but rather I'm just extracting the term that is the biggest, so the one that has the most influence on the value of the polynomial. So if I've extracted x to the n, this term is becoming infinite, and all terms within our parentheses that have x at their divisor are tending towards 0 because they are of the k over infinity form. You've got a constant over something becoming infinite. So essentially all that's left is infinity times the constant an. So the outcome will be infinite in size if an was a positive coefficient, or potentially could be minus infinity if an was a negative coefficient. Likewise, as x goes towards minus infinity, we could use the same process, which is to extract the term with the biggest power. This term will become infinite in size, but in terms of its sign, depends on whether n is even or is odd. Once again, all terms divided by powers of x that are growing, in this case, will go towards 0. And then we can expand infinity or distribute infinity to the constant an. The answer will be plus or minus infinity. This time it depends on the combination of signs and on whether n is odd or even. Graphically, here is a first-degree polynomial, so a line. It's clear that it is heading towards infinity at the extreme right, heading towards minus infinity at the extreme left. Parabolas will have an extreme behavior at both extremities. Both edges go to minus infinity if the parabola is concave down, or could be heading towards plus infinity if it had been concave up. Here's a third-degree polynomial which has extreme behaviors at the extremities. So the function is going to plus infinity at the extreme right, minus infinity at the extreme left. And even in the case of fourth degree polynomials, we see that this standard is maintained, where we've got infinite behaviors at the extremities.